Hello people, welcome back to this video. So we're gonna continue where we left off. So we're trying to find an expression for shear stress. Unfortunately, this is in sort of the how do you put this? It's in the sort of the format, or it's in terms of this boundary layer thickness, which we don't really know at all. Okay. We don't know what the boundary layer thickness is, like based on our input variables. So we still need to like solve for this boundary layer thickness thingy. And of course, the way to solve it is to substitute out the shear stress. Why does that help? Because when you substitute in this side, you will be able to find an equation that only depends on x and delta p. So without further ado, let's continue this. Okay, what is del u del y? What is del u del y? Let's see. Del u del y. We have done it before. Okay. Del u del y. Okay. Shear stress. Okay, let's see. Partial u. Yeah, looks like some alarms going off. I don't know if you can hear it, but I do apologize if it's annoying. Okay, so let's have a b. Okay, b is 3/2 delta p u infinity, and c is 0 conveniently. Okay, c is 0. D, that's 3d delta p 3. Excuse me. 3d delta p square. 3d delta p square. So what's delta p square, or what? Yeah, what's d first? Let's go. Oh shucks. D is okay. D is minus u infinity minus fraction u infinity over 2 delta p cubed. Alright, so let's simplify this quickly. Okay, so of course the delta p's will cancel out, and then we'll get a 3/2 in front. Okay, 3/2 in front, so it's a minus 3/2, minus 3/2. Okay, delta p will be at the bottom, and we'll cancel out that delta p squared, and that's what you have. Okay, so oh wait, isn't this just 0? Okay, hold on. Am I getting something wrong? Del u del y. Three delta p squared. Okay. I think I substituted some things wrong. Let's see. Yeah, okay, this is del u del y. There should be a y squared down there. So sorry. I should not put delta p in there first. So the second term will disappear. I'm so sorry. D is again. Okay, let's try this again. On top should be y squared. Yes, you don't substitute the delta p, because the shear stress there will be 0, which is right. Okay, so this whole second term disappears. Second term here disappears because y equals to 0. Alright. So we are substituting. Yeah, we're substituting y equals to 0 because we're interested in the shear stress at the wall. Okay, so we are interested in the shear stress at the wall. Okay, so we find tau x at y equals 0. So this is what we need to substitute because we want the shear stress at the wall. So just to make things clear and to avoid confusion, let's put y equals 0 here. So this is the correct boundary condition. Okay, tau x at the wall, and that's what we are interested in finding out. So this is what we are substituting out. Okay, I just want to make it very clear. Make it very clear here. Okay, so no confusion here, yeah? Okay, of course you can make the substitution all the way up. I'm not going to replace all the notations here. Yeah, but all of this actually means the shear stress at the wall in the x direction. So this y should be equals to 0. Okay, so that's why we have the partial u partial y. So remember what we want to find here is tau wall over rho. So tau wall over rho. Okay, fraction tau x wall over rho naught or rho equals to nu and del u del y at y equals to 0 equals to nu times whatever this is over here. Okay, so now we have this expression. We can just plug that back in here. Substitute back. So this expression we will use right here. And now we have a very simple-ish expression. Of course, this one you can do some multiplication over. Oh yeah, I think I want to get rid of this part. Okay, tau x wall over rho is equals to this. You just substitute wholesale. So we can cancel the u infinities out here and here. Cancel out the u infinities. And 3 over 2 can be multiplied over, so you multiply both sides by 2, this one becomes 140. 140. Okay, so I'll get rid of the 2. And you divide both sides by 3. So 39 divided by 3. Oh, it's just a very nice round number, right? 39 divided by 3 is just 13. So, and you see the delta P doesn't quite cancel. But you can actually bring some of the derivatives over. Okay, so there's a 1 over delta P here. Okay, so we assume all of this is constant. Nu is constant, and u infinity is constant for this flat plate flow. Okay, so we can change this into a total derivative, and we can just perform separation of variables and just integrate over the whole boundary layer. Alright. Okay, so after that we can just do separation of variables. So we'll bring delta P over to the other side, and we'll bring 140 over 13 to the left hand side. So delta P goes to this side, and the x goes to the left hand side. And u infinity and all of that, that can be on either side, doesn't really matter. Okay, so delta P goes to the right, u infinity, I'll just leave it there. Okay, oh yes, I forgot, d delta P, sorry, d delta P. Okay. Alright, so very simple. Very simple now. We just perform integration. Okay, integrate. I integrate x from 0 to x, I guess. Okay, I integrate the left side from 0 to x. The right side I will just integrate from, well, when x equals 0, there's no boundary layer thickness, so delta p x equals to delta p equals 0. Then when x equals to, that's x, okay, along that line, delta p will just be the boundary layer thickness at that point. Okay, so I mean there's a proper way to do this. We're actually supposed to change the limits. Okay, the limits are correctly called x, but you are not really supposed to integrate like this. You're supposed to swap out for something called dummy variable. Okay, in proper math notation, we have to use dummy variables. Okay, dummy variable. So this x should not be called x. So we'll just because we are integrating to the point, we are integrating to x. Okay, wherever x is in that boundary layer. So let me bring out GIMP. Yeah, we are actually integrating this equation all the way to the boundary layer where x equals to x, right? So I don't know where is this okay, let me get y. Yeah, so this is along the x-axis. We are performing this integration from 0 to x for the left hand side. 0 to x. Okay, x is some arbitrary point of our choosing, and of course at x, the boundary layer delta p will be delta p x thick. Okay, for this one is a momentum boundary layer. Okay, or whatever. Let's see how much time I have left. Okay, still got a while, 8 minutes. Okay, so I'm supposed to swap this out for about dummy variables. So I will replace x with x prime and delta p. Everywhere delta p appears, I'll just use delta p prime, just to, you know, to make the math notation more proper. So this is the proper math notation. Now after that, performing integration is relatively easy. Okay, so this part becomes just x itself, and this one becomes delta p x, or delta p x squared over 2. All right. Okay, let's do a fraction, delta p x square over 2. All right. Alright, so let's bring the 2 over. We'll get a 70 on the... No, you don't get 70. We'll get 280 again. 280. That's bringing 2 over. And then we'll sort of have to do a square root. Okay? And of course, you'll notice something. You have u infinity x and nu here, so you can sort of see a Reynolds number forming. But just to make it more obvious, let's make delta px the subject. Okay, delta px equals, okay, square root of 280 over 13. And what do you have? Nu x, nu and x on top, and you have u infinity at the bottom. So it's like a 1 over the Reynolds number, almost. Huh? Because usually Reynolds number x and u infinity are on the same side, so we will need to do something. So if you want to make it look like a Reynolds number kind of thing, x must be at the bottom. So, and then to compensate, you kind of need x squared on top. Okay, so multiply both sides by x, okay, and then bring the x squared out. We will get this expression for the boundary layer thickness, 1 over x. Okay, and now you have a Reynolds number like Rex over here. So the last step will be like so. This is actually 1 over Reynolds number using, I went too far bottom, Re and x. Okay, so you want the 280 over 13, you'll give the square root. Okay, equals square root 280 over 13. Okay, 4.64. Okay, that's what we get. So if we take this out, and then we'll get 4.64 something. 4.64 095. Alright. So this is how our boundary layer changes with x, and of course Rex is ux over nu. Okay, where Rex equals to u infinity x over nu. All right. So this is how our boundary layer thickness will change. And now that we have this, we can simply substitute all these things back to get our shear stress. Okay. Fraction tau x wall over rho equals to nu del u del y at y equals to 0. And this is what we will use right here. Okay, so I'm just presenting some of the results. Okay, let's see how much, not that much time, but not that little as well. Not great, not terrible. Okay, anyway, so let's put this expression in, and of course you see it varying with x. So I'm just going to copy and paste delta p in. So delta p over x is this, and then you just multiply by x, and this will be your wall shear stress expression. Where's that 24? Oh, I need a times here. Okay, nothing too exciting there, but this is what your wall shear stress will be like. Interesting thing, we usually like to calculate skin coefficient of friction. Okay, CF. Okay, so this is the local coefficient of friction. Okay, how does this go? CFX. Okay, so this is from the textbook. It's equivalent. This is a definition. Okay, tau x wall over half rho u infinity square. Okay, so we want to multiply all of this in, and of course, since we have tau wall over rho already, we just need to divide the whole thing through by half u infinity square. So we'll put half u infinity square at the denominator, or maybe, yeah, it's pretty much just 2 on top, because that's how, yeah, this one you'll come on top, and then you'll multiply by this whole thing over here. Okay. Okay, so not too bad. These tools will cancel out. and then 3 over this 4 point something something will give you a number. Okay, and some of the u infinities will cancel out as well. Okay, some of the u in fact you can actually make another Reynolds number there. Okay, but let's do 3 over 4 points, that whole thing there. Okay, so man. Okay, never mind. Let me try again. I kind of lost my marble. I don't know whether to use the term "lost my marbles" is the correct way, but never mind. Let's cancel again the 2's. Let's cancel again the 2's, and we'll have a 3 over 4.695. Okay, equals to 3 divided by this number, 0.6464. Okay, that's a nice number. Let's put 0.6464 in front, 0.6464, and let's get rid of this. Okay, and of course the u infinity we can cancel out. Let's cancel out u infinity. U infinity will be cancelled out. And lo and behold, the Reynolds number appears again. Okay, u infinity x over nu. Okay, u infinity x over nu. So this is actually just the Reynolds number that appears at the bottom. Rex again. Rex. So let me get rid of nu and u infinity. Alright. Okay, this is the weirdest looking fraction I've ever seen, but I'll just leave it as it is. Then after that, you just have square root of Reynolds number at the bottom, and that's the skin friction coefficient, and that's how we derive it. Okay. Then there's the average skin friction coefficient. Alright, so how do we have this average skin friction coefficient? Okay, we call it C, some people call it CFL, because we're averaging. And how is it being averaged? So it's defined as the following. Okay, fraction 1 over L, integrate from 0 to L dx of CFX. Okay, simple. I mean, I hope it's simple. Okay, so this is how it is defined, and to do this we'll need to like integrate out some of the Reynolds number. Okay, so we'll just copy and paste this here, and let's see how much time I have. Oh man, okay, so I will continue in the next video. We'll do this integration in the next video, and I'll see you guys next time. Okay, running over time again. Bye bye.